Okay, so multiple choice 18 asks, which of the following is the major product of the reaction shown? So as we remember from the last exam, Br2 over H2O / any variation of OH, so ROH, is going to add a Br anti to the CH3OH. Okay? Or to the H2O or to the OH. So Br adds anti, in this case, to the CH3OH. And as we remember from like the whole BLAM situation, the acidic things are going to want to attack the more substituted sides. So the alcohol is going to attack the more substituted side. So in this case, CH3OH attacks more substituted, oops, hopefully you guys can hear me, more substituted side. Okay, so I'm going to erase and we can go ahead and do the mech. Okay. Okay, so you're going to start obviously with your starting material and Br2. You're going to get the ring that's going to form between the Br. Oops, that's kind of sloppy. And then the rest of the electrons are going to go to the other Br. Okay. So now your bridge, you're going to have a bridge formed with the Br. You could either put it on wedges or dashes because technically you're going to get both. So everything from here on out will be plus the enantiomer. Okay. So then the next step, I will get the starting material ready. CH3 is going to be the addition of the CH3OH. Okay, oops. Okay, and this is going to attack the more substituted side, which is going to push the methyl down to a dash in this case. If the methyl was on a dash already, it would push it up to a wedge. So when the OCH3 or H2O or OH attacks, just know it's going to flip the stereochem of the methyl, and this is going to open up the ring, pushing the Br over. The Br will retain whatever stereochem it had here. So your product for this step is going to look like this. And it's going to be protonated still. The methyl will be on a dash, and the Br will be on a dash. So the Br will always be syn or cis to whatever was originally on the ring. And then you're just going to deprotonate, so to save time I'm going to write H-, and you will get OCH3, the methyl, and the Br, and you'll also get the enantiomer, which will look like this, OCH3, methyl, Br. So now, keeping this in mind, all we have to do is convert this to the most stable chair conformation, and when you do that, you end up getting C. So in case some people have trouble or difficulty converting from the ring to the chair, I'm going to go over that really quickly in case. So we'll go ahead and draw our chair. And the first thing you want to do is draw your axial and equatorial lines. So the first one we're going to make axial up, equatorial down. So the second one is going to be axial down, equatorial up. And then we are going to draw another chair just in case we have to convert. Same situation, axial up, equatorial down, equatorial up. So if we're looking at this one and we're converting it to the chair, I'm going to use the wedges up for the first one and then the dashes as down. So the OCH3 is going to be coming off of the top. The CH3 is going to be going down, and the BR is going to be going down as well because it is cis to the CH3. So that doesn't look exactly like ours, so we actually do have to flip it in this case. So you're going to flip to get the OCH3 equatorial because this is more stable. Since the OCH3 is larger, anytime you have a larger molecule, that's going to want to go on equatorial. So that's a reminder. I know some people got that wrong. So larger molecules prefer to be equatorial. Okay, so OCH3, then we're going to put the CH3 up here. Since the BR is cis to it, the BR is also going to go up, and that shows you the answer for C. Hopefully that helped, just in case it's been a while since you guys have drawn chairs and done chair flips. Okay, so multiple choice 19 asks, of the following compounds, which would have the highest boiling point? I went ahead and I just drew in the boiling points for all of these anyway. So the first one is going to have a boiling point of 36. The second one is going to have a boiling point of 9 degrees, even though these have the same amount of carbons. Wait, let me double check. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4. Yeah, so in general, even though these have the same amount of carbons, increased branching is going to increase boiling point. Reason being is when you're thinking about boiling point in general, highest boiling point is the same as asking which H bonds or hydrogen bonds most. So when you have branching, you have more access to hydrogen bonding because all of these H's are out here. Okay? So increased branching equals increased boiling point, so that's why B is going to have a higher one than A. C is going to have the highest one because you have an OH, and OH has really, really good hydrogen bonding. Then the ether, the only reason why this would be lower than the, how would you pronounce it? Diethylamine or something like that. I don't remember the name. It's like N-dimethylethylamine. There you go. So the reason why the ether has a slightly lower one than that one is because this O is kind of protected. So that's a little bit of a fun fact, I guess. But they're almost identical. You would never really have to pick between the two of them because depending on the textbook, they're sometimes ranked at the same boiling point. But the big one that you were supposed to notice was the OH, or carboxylic acids would have higher boiling point, or aldehydes have pretty high boiling point. Anything with an O has a really high boiling point because they're able to H bond. So C is the right answer because increased H bonding. Plus it's also a conjugate of water, so that's how you know that it's going to have really good H bonding. So for number 19, the answer is C. Okay, so number 20 asks us to rank the following molecules according to increasing length of the indicated bonds. Shortest first, longest last. So the only interesting thing about this one compared to other bonds length questions that we've asked is that now we have benzene as one of the bonds that we're comparing. So in general, when you're thinking of bond length, the trend is as follows. So sp are going to have the smallest bond lengths, then sp2, then sp3 are going to have the largest bond lengths. Obviously, a C bonded to an H is going to, this bond length here is going to be smaller than all the other ones, smaller than a C to C triple bond, smaller than a C to C double bond, and smaller than a C to C single bond. So I'm going to erase that. And the interesting thing about benzene is actually between. So when you're thinking about sp characterization, benzene, ignore my dog snoring, benzene is between sp2 and sp3. So it would be right around here is benzene. So drawing this using words, so you're going to have triple bond, then double bond, then benzene. I'm running out of space. Okay, then benzene, then single bond. Okay, so now we can go ahead and look at our answer choices here. So the first one is going to be a triple bond, and considering all the others that we're comparing it to, actually I can keep that. Considering the others that we're comparing it to, the triple bond is definitely going to be the smallest, and they did say in order of increasing, so you can eliminate any answer choices where 1 isn't the first option, so D and E. Now we can look at number 2. Number 2 is just a regular single bond, and given the choices we have, that's going to be our longest one, so you can eliminate any where 2 isn't at the end. So that's going to eliminate A. Looking at 3, this is an sp2 carbon, and 4 is between sp2 and sp3. So that means 4 is going to be a little bit bigger than 3. So now we know that 1 is the smallest, then 3, then 4, then 2. The answer choice that matches that is going to be C. So just make sure you remember that benzene is between sp2 and sp3. So it's bigger than sp2, smaller than sp3. I'll write that down. Bigger than sp2, smaller than sp3. So the answer to 20, like I said, is going to be C. Okay, so number 21 asks, which reaction generates the major product shown? So you have to know what all of these reactants do and if the product is correct or not. So if you guys have been checking the key for this came from, I believe, the fall 2007 exam of O'Connor's old exams for 307. There was a mistake in this key. They put the answer as A, but it's actually E. And I'm going to go ahead and go into why. So when you are treating a alkyne with H2SO4 over HgSO4, you will never get an aldehyde. You're going to always get the ketone formation. So for this answer choice, the product would have looked like this. Let me count my carbons and double check. 1, 2, 3, 4. 1, 2, 3, 4. Yeah, so if you're using H2SO4 over HgSO4, it prefers to form the ketone on the more substituted side, so you're not going to get an aldehyde from this, so that is why A is not the correct answer. So looking at B, this is one of the special little tricks or the special cases of, why am I using that color? The special cases of reaction. If you treat an alkyne with 2 HBr, you're going to get 2 BRs on one side of the alkyne. So it's going to look like, oopsie, it would look like this. Okay. It would look like this instead. If you treated it with 1 HBr and then another HBr, then you would get that product. Because each time you add an HBr, you're going to remove a bond and add the Br. So this would have been B's product. But if you treat them all in one shot, you're going to get both of the Brs on one carbon. If you treat them one at a time, then you would get B. Okay. So the intermediate, just for reference, would be a one. How many carbons is this? 1, 2, 3, 4. It would have been something like this, or on the more substituted side. And that would have been how you would get to this later, if you treated it again with another round of HBr. But 2 HBr on an alkyne is like a known little oddball case. So just make sure you remember that if you treat an alkyne with 2, it's going to add to the same carbon. Okay, so B is not the answer. Okay. C shows you going from a alkyne to a cis double bond. The reaction that does that is the one that uses Lindlar's. H2PD or PT, you can use either one, would give you, all right, let me redraw that. H2PD would give you the trans version, so let's count carbons. 1, 2, 3, 4, 5, 6. You would get this 6 with the double bond between 3 and 4. So this would be if you treated it with H2PD, but that's not the reaction answer that they show. So you can eliminate C. All right, now D is another alkyne case where you get the alkyne to a enol. In this situation, though, if you use disamylborane, you're going to get the aldehyde product instead of the ketone product. So I'm not going to write the whole thing. I'm just going to write diasam and quotes for the rest of the reaction. So if you treat a alkyne with diasam, and especially if it's terminal, you're going to get the aldehyde. So it would look like this. 1, 2, 3, 4, 1, 2, 3, 4. Yeah. So that would have been the product for D, but unfortunately that's not what they showed, so you can eliminate D. And then finally, this one should have been pretty easy because NaNH3 very obviously converts a triple bond to a trans double bond. So if you're converting a triple bond to a trans double bond, you can count the carbons. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. And your product, oops. Weird. Okay. My iPad has given up. Your product would look like this, and that's exactly what you have here. So the answer to 21 is going to be E. Okie dokie. So multiple choice 22 asks us to rank the following carbocations in order of increasing stability. So that means the least stable is going to come first, and then the most stable is going to come last. So really quickly, carbocation stability and the things that impact it. So the least stable things are going to be vinyl carbocations or anions. And these are carbocations that are located directly on a double or triple bond. So then the next thing that's going to, all right, actually, let me write this down. Least stable. Other things that impact carbocation stability is how highly substituted the carbocation is. So tertiary carbocations are going to be more stable than secondary and primary. So I'll draw out secondary. And then finally, primary. Okay. And then underneath, tertiary carbocation are more stable than secondary, and secondary is more stable than primary. Primary carbocations. Okay. And then there's one other factor that impacts carbocation stability. So I'm going to go ahead and erase, and then I'll include it. Okay, so the next factor that affects carbocation stability is resonance. So, for example, this carbocation is going to be less stable than this one because this one can resonate. I'll draw the resonance in, not in that color. Okay. That being said, you can also rank resonance. So I'm going to erase really quickly. Okay, so if you have a carbocation next to a benzene, this is going to have really, really good stability because it can resonate with the benzene molecule. So this is going to be highest resonance stability. Then we have just your average carbocation resonance with a double bond nearby. However, if you have a carbocation like this, oops, let me erase. Say you have this situation. This is going to be your least resonance stability. That's English, but you know what I'm trying to say. Because when this resonates, because your double bond is terminal, when this resonates, you're going to end up with a primary carbocation. So comparing these three resonance structures, this is going to be number 1, this is going to be number 2, and this is going to be number 3. It's important to keep in mind not only that there's resonance nearby, how the carbocation is going to look after it resonates. Okay? So those are some of the things that impact carbocation stability. Now we can go ahead and start this question. Okay, so looking for anything that pops out as weird, we see that number 2 is a vinyl carbocation. And these are statistically like the least stable carbocations. They're even less stable than primary. So we should eliminate any answer choice where 2 is not the first one. And that actually gives you the answer of A. But we can go ahead and keep ranking them. So 2 is going to be our first one. And now we can go ahead, I'll do a different color. Now we can go ahead and look at the other ones. So 4 is just a regular sp2 carbocation. And 1, 3, and 5 are all sp2 carbocations that can resonate. So that means since 4 doesn't have that resonance ability, 4 is going to go next in order of increasing stability. Because resonance contributes to higher stability. 4 doesn't have any resonance, so it's going to be next. Okay, so now comparing 1, 3, and 5, these are all carbocations that can resonate. We can draw out the different resonance structures for 1 and 3, and 5 is a benzene resonance, and as I told you, that's going to be your highest stability of resonance, so you know 5 is going to be at the end. Comparing 1 and 3 now, what they're going to look like when they resonate. Oops. So this is 1, by the way. 1 is going to end up with a primary carbocation in its resonance. And if you draw out 3's resonance, it is going to give you another secondary carbocation in both resonance structures. So that means 3 is going to be more more stable than 1. So 3 is going to be more stable than 1. Yeah, I'm so sorry. I was looking at the answer choice and for some reason I didn't understand the arrows that I drew for a minute. So maybe because we're going in order of increasing. All right, so like I said, the answer is going to be A, and the reasonings that we found also support the answer. Oh, really quickly, another way to think about this is that 1 is going to be a shorter allylic bond. Some people will refer to it like this. 1 is a shorter allylic bond than 3 is. Okay, now I'm done. Those are all the points that I wanted to get past. Okay, so multiple choice 23 was actually an exam question from your last midterm. Your last real midterm, not a mock. But we'll go over it anyway, just in case people had issues with it. And this was on his old final, so you never know. I actually do think this final is worth going over. I'll include it at the end in case you guys want to do it. So really quickly, let's go through number 23. So the first step is that they're going to treat our reagent with tosyl chloride and pyridine. So tosyl chloride and pyridine will not cause inversion. However, it will replace an OH with a Cl. Make sure you just remember that stereochem does not change when the OH is replaced with the Cl. Let me rewrite that. Okay, so now we can go ahead and draw in our first product. I'm going to erase. Okay, so product number 1 is going to be, so you start with this, then you treat it with tosyl chloride and pyr, and this is going to give you this product. I'm going to zoom in so I could actually draw it neatly. Okay, so that's going to be the product of the first step. And then step 2 is actually going to be an SN2 reaction. So that means you're going to have the inversion and the one-step reaction. And tosyl chloride is the good leaving group, so it's going to replace tosyl chloride with CN. So I will write that down really quickly. So step 2 is, let me write it like this, is an SN2 reaction. So you will replace the good leaving group, in this case tosyl chloride, with the nucleophile, which in this case is going to be CN. Okay, so I'll erase. And then let's go ahead and fill in step 2. So like I said, just make sure you remember every time you do an SN2 reaction, you're going to have the inversion of stereochem. DMSO is a polar aprotic solvent, also characteristic of the SN2 reaction. So our final product is going to look like this. Okay, so let's see what answer choice that matches. And comparing the answer choices to what we have, we see that E has an OCN, so that's not going to be it. D is a elimination reaction, which isn't what we had, so that's not going to be it. C is going to be the pair of an enantiomer, or in this case diastereomers, so that's not going to be it because SN2 reactions give you a full inversion. E is if you didn't switch the stereochem, or maybe if you switch the stereochem twice. And A is going to be the correct answer because it matches our product here. So the answer to multiple choice 23 is going to be letter A. Really quickly, I did just want to note that a lot of these exam questions were from the old O'Connor exam that was Orgo 307, fall 2004 final exam. So this is going to be under the old exams, and it's all multiple choice, and there were a lot of really good questions on this exam that I didn't get to fit in the mock because I know you guys are probably tired and I didn't want to make this mock too long. But if you have the time, there is a key actually handwritten out with it as well. So I think it's really worth looking through the old multiple choice final exams on Sakai. If you have any trouble finding them, please feel free to ask me. But these ones specifically were for this exam, and there were about like 25 other ones that I didn't get to use that were also really good and representative and will honestly probably show up on your exam. So I highly recommend looking at this exam before your actual final on Monday. Okay, so 1x asks us to write the complete mechanism for the formation of the major product of the following reaction. Label the thermodynamic and the kinetic products. Be sure to include all resonance forms of the intermediate. Also, make sure that you show all charges, lone pairs, and the movement of electrons with appropriate curved arrows. Okie dokie. So in this one, because your double bonds aren't equivalent, so this one is tri-substituted and this one is not, you want to figure out which double bond is going to give you the more stable carbocation resonance intermediates. So go ahead and off to the side somewhere, because this isn't actually part of the exam question, draw the HBr adding to either side or either double bond, either side of the molecule or either double bond. Let me finish my sentence. So let's go ahead and try using the more substituted double bond first. So the way HBr adds is you're going to add the H to the less substituted side, leaving the carbocation on the other side, and then the Br will add there. So if we add the H to the less substituted side, the H will be added here. And the carbocation is going to be here. Now, the issue with using this double bond here is that now we can't actually resonate because the double bond is too far away from the carbocation, so it's not going to resonate. So you actually can't use this double bond for this question. You actually have no choice but to use the second one. But let's go ahead and try it just in case. Make sure that we can do proper resonance if we use the other one. Okay, so say we add the HBr to this double bond, the H is going to add to the less substituted side, and then the carbocation is going to be on the more substituted side. So going ahead and doing that, your H is going to add here, and your carbocation is going to be here. And this is going to be the better choice of double bond because, let me do this in a different color. Now this double bond can resonate with the carbocation, and you will get this as your second resonance structure. So the double bond that you have to use when you're doing this question is going to be this one. Okay? Hopefully that made sense. Okay, so now we can actually start the real mechanism. Really quickly before we're doing this, because they're going to ask you which one is the kinetic and the thermodynamic product most of the time. So the thermodynamic product is going to be the product with the more highly substituted double bond. Okay. The kinetic product is going to be the product that comes from the more highly substituted carbocation, which is the same thing as saying the product with the more highly substituted halogen. So in general, the kinetic effect will apply here, but say that the kinetic effect, or like the proximity effect, the kinetic effect. So in general, the proximity effect will happen to show up in the way that the halogen will be more substituted and the H will be nearby. But if it comes down to choosing one where the proximity effect is how do I explain this? Okay, so say you have this, right? Say you have this as one of your answers and this as one of your answers, where the H is going to add here for both of them, hypothetically. Although this one is going to feature the proximity effect because the H and the Br are closer, and 9 times out of 10, like when you're doing the kinetic product, it's going to also satisfy the proximity effect. So a lot of times they'll just say, oh, the kinetic product also shows the proximity effect. However, there will be cases where you'll have to pick between these two. You're always going to want to pick this one because this one's going to have the more highly substituted halogen. Every single time you're asked for the kinetic product, it's always going to be the more highly substituted halogen, even if maybe the proximity effect is displayed in a different answer choice. Okay? So if this makes no sense to you, don't worry about that, but I did have a question about that once where one of the answer choices had the proximity effect and one of them had the more highly substituted halogen. You're going to go with the more highly substituted halogen before you're going to go with the proximity effect. So like in ranking, it's more important that you have the more stable carbocation, aka the more highly stable halogen at the end, than it is that you have the proximity effect. The proximity effect is more like a side feature. It's like an observation that most of these products will also happen to have. But it's not a requirement, if that makes sense. Okay, now that my little rant is over, I'm going to erase, and we can do this question. Okay. So now that we know which double bond we're going to use, we can go ahead and treat it with HBr. So I'm going to do this in dark blue. Okie dokie. So the electrons from the molecule or the double bond of your choice are going to come and pick up the H from the HBr. These electrons are going to come and move over to the Br. So you're going to have this as a product, where the H is going to be added here. That's kind of sloppy. Let me redraw it. And then you're going to have the Br anion. So now what you're going to want to do is draw the different resonances of this molecule here. So for space purposes, I'm going to erase the, for space purposes, I'm going to erase the Br anion and go ahead and draw the resonance. Okay, so if we're moving this one over, I'll do resonance in a different color so we don't get confused. So if we're moving the double bond over one space, this is going to be the resonance form. Okay, oops. So these are going to be your two resonance contributors. And now you have to figure out, okay, well, which one is going to give me the kinetic and which one's going to give you the thermodynamic. Since this one has the more highly substituted double bond, this will give you the thermodynamic one. Since this one has the more highly substituted carbocation, which is going to make the more highly substituted halogen, this is going to give you the kinetic. Oh no. Okay, so kinetic, thermodynamic one. And then you can go ahead and move on to the next steps of the mech. So I'm going to start using the thermodynamic intermediate and add the Br anion back to that one. Of course, the Br is going to add to the carbocation. Okay. So it's going to add here. So this is going to be your thermodynamic product. Okay, so now we're going to use the other resonance conformer and go ahead and do the kinetic product. So this is actually going to be an example of when the proximity effect is not as important as the fact that the halogen is more highly substituted. Because your H is going to be here, and your halogen is going to add here. So although these are far away, this violates the proximity effect, but because your halogen is still more highly substituted, that's more important than the proximity effect. So just keep that in mind when you're doing kinetic products. Make sure you look for the fact that the halogen is more highly substituted, not the fact that the halogen adds close to the H. Because here you see that the halogen does add close to the H, but this is a rare exception to the rule. So just keep that in mind. There will be cases like this where the proximity effect is not fulfilled. But in general, if they're going to ask you for features of it, just say that, oh yeah, okay, so the proximity effect is a factor of kinetic, because more often than not it is. Okay, so let's go ahead and keep going. So now we're going to add our Br anion. This is going to add to our carbocation ion. And your product is going to look like this. So like I said, this is going to be your kinetic product. Okay, so this is the answer to 1xa, and then we can move on to 1xb, which is mostly conceptual. Okay, so part B says, with reference to the above reaction and the aid of appropriate diagrams, explain the difference between the thermodynamic and kinetic products and the reaction conditions leading to an excess of one or the other. Okay, so for this one, although we've went over this together conceptually, I'm going to give you O'Connor's exact answers because O'Connor's the one who makes the exams, so it would be most beneficial if you guys had his reasoning or his thought process. So first he draws out the thermodynamic product and the kinetic product for the above reaction. So the thermodynamic product is this one. Okay, And then he says that this is the more stable alkene, which is the same thing as saying that this is the more stable product. So now we have the kinetic product. And then he writes underneath, featuring my dog in the background, but he writes underneath that it is made faster. And then he draws this product from before. And then he says that it is made from the more stable carbocation intermediate. So then he writes that the thermodynamic product is made in excess under high temp conditions or under high temperatures. The kinetic product is favored in excess under low temp conditions. Oops. So now we have to move on to the graph. So let's go ahead and draw it. I'm actually going to draw it down here. Okay. So on this side you have delta E. On the bottom you have reaction progress. And then I'm going to use different colors. Which ones am I going to use? Okay, so we'll do red and blue, so purple will be the intermediate. So they're both going to follow this first part, and then this is where they're going to split off. So the thermodynamic product is going to come and go up here. So this is the thermodynamic. And then the kinetic one is going to have a lower activation energy, but a higher final energy. They're both going to be exothermic with respect to the starting energy, but the kinetic product is going to have a higher finishing energy than the thermodynamic product will. And the thermodynamic one is going to have a higher energy of activation than the kinetic product will. Okay? Okay, so let's go over his explanation. So low temperature allows for reversal of the kinetic product back to the intermediate. Oh, no. He messed this up. This is supposed to be high temperature. So high temperature allows for a reversal of the kinetic product back to the intermediate. And this will give it the opportunity to go to the thermodynamic product. So the high temp then allows for the intermediate to reach the high activation energy. So activation energy abbreviated by EA of the thermodynamic product. So yeah, important side note that the kinetic product is reversible, while the thermodynamic product is not reversible, because the thermodynamic product is more stable than the kinetic product. When you're less stable, you're going to have a higher chance of going back to the intermediate because you're not that stable of a product. When you're really, really stable, it's very unlikely that anything is going to change about you, so you're not really going to revert back to the intermediate. Okay, let me see if there's anything I'm missing. Due to low thermodynamic, easily reversed. Yeah, so basically he says that the thermodynamic product is less easily reversed than the kinetic product. Which is what I just said. Product less easily reversed than the kinetic product. Under low temperatures, the high activation of the thermodynamic product, so the high activation energy EA of the thermodynamic pathway is harder to reach, harder to meet or reach, whatever. So the kinetic product is favored because it has a lower activation energy. Okie dokie. So that is the very long answer to part B. This is the second part, and this is the first part. So hopefully that makes sense. If you guys have any questions, as usual, let me know. And yeah. Okay. Sorry, so number 10 I accidentally left off because I thought this was about ethers, but looking at it again, I realized this is actually relevant content for your exam. So the answer to number 10 is going to be D. Reason being, so the question asks which of the following reactions will produce the major product shown. So the reason why D does produce this product is because it has the primary alkyl halide. So hold on, let me erase. So this is your primary alkyl halide. And then you have your nucleophile here. So this nucleophile is a strong nucleophile because it is charged. And then you have your polar aprotic solvent. So looking at all of these are all characteristics of a SN2 reaction. So all we have to do is make sure that the product is an SN2 product. And in this case, you do get the SN2 product with the one-step replacement. So the answer to number 10 is D. All the other ones do not give you the correct product. So hopefully that helped. If anybody wanted any explanations of why the other ones don't give those products, feel free to ask me at any time. Okie dokie, so that's going to be the end of the mock. And I just wanted to remind you guys to definitely check out the other old exams on the Sakai. If you have any questions about them, please feel free to ask me at any time. Definitely write down the questions you didn't know and print out all of these exams. I saw a lot of you guys were sending me either digital or written out versions of these. I genuinely think if you have access to a printer, it is worth printing these out so that way during the real exam you can reference them really easily, or maybe keep them all under one folder on your iPad. But a lot of you guys were just writing the answers on a piece of paper, and at the end of the day, that's not going to help you during the real exam. So I do recommend printing it or keeping them online, whatever works for you, with the answers so that you can access them really quickly. Other than that, yeah, make sure you do your reaction sheet. If you guys want, you can drop them on GroupMe and I'll check them over and see if there's any extra reactions I would add. And I do have some reaction sheets also uploaded on Sakai, some example reaction sheets. One that O'Connor himself made of all the useful reactions, so I would definitely check those out if you haven't already. They're under the Orgo 307 tab. Again, if you have trouble finding them, you could totally ask me. And I just wanted to take a minute to say thank you guys for letting me help you guys out this semester. I really appreciate having the opportunity to teach you guys, and I know it's been disorganized from day one with not knowing exactly what was going on and then having everything been online, but I really genuinely did try to do my best, so I really hope that you guys do well in this final and take it seriously and get the grade that you all deserve. So thank you very much. I also wanted to say that I put in participation grades and I did give you guys all an A because I genuinely feel that you deserved it. Most of you, if not all of you, came to every single session, even online or in person, always participated, asked me questions, sent me the exams. So I really appreciate all the work that you guys did as well, and I genuinely wish you the best. And if you have any other exams that have been giving you trouble, you could always ask me, if not now, in the future. I have like old exams for a lot of different classes. So please feel free to reach out if you ever need help. Like, I will be around, even though I'll be physically not in New Brunswick. So thank you guys so much, and hopefully we do well on the exam together. Bye.